Welcome everyone, and thank you for joining us today. I'm excited to present our submersible pumps design and installation presentation. The focus of today's session is on the system for drainage and sewage submersible pump sets. On this slide, you'll see a visual representation in Revit 3D, showing a top view of both pumping stations, including the Grundfos pumps and control panel locations. Over the next few minutes, we'll explore the key design considerations and installation practices for these systems. So, let's get started. Let's take a closer look at the design requirements for our drainage and sewage systems. These systems are engineered to operate continuously under a 400-volt, 3-phase, 60 Hz power supply. Each system includes one duty pump and one standby pump, ensuring reliability and uninterrupted operation. For the drainage pump, we're looking at a flow rate of about 6.59 liters per second, with a head of approximately 15.61 meters. It consumes around 2.2 kilowatts of power. On the other hand, the sewage pump has a slightly higher flow rate, 7.05 liters per second, and operates at a much higher head of 41.5 meters, with a power requirement of 11 kilowatts. Now, the hydraulic design follows some fundamental principles. Q represents the flow rate in liters per second, H is the total dynamic head in meters, and P, which is the power, is calculated using this formula involving the fluid's density, gravity, flow rate, head, efficiency, and a constant factor. It's also important to note that our system complies with several key standards, including SBC 801, NFPA 20, and IEC 60204. These standards ensure safety, efficiency, and reliability across our design. Overall, these specifications and standards form the backbone of a robust, efficient, and safe drainage and sewage system, aligning with our goal of building resilient infrastructure. Let's take a closer look at how we calculate head loss and the total dynamic head in our hydraulic system. We use the Hazen, Williams method for these calculations, which is quite popular for water flow in pipes. The head loss, denoted as HF, is calculated with this formula. 10.67 multiplied by the ratio of the pipe length, L, to the Hazen, Williams coefficient, C, raised to the power of 1.85. Then we multiply that by the flow rate, Q, raised to the same power, 1.85, and divide everything by the pipe diameter, D, raised to the 4.87 power. Once we have the head loss, we add it to the static head, or the initial height of the water, and include an additional 25% safety margin to account for uncertainties or future expansion. The total dynamic head, or TDH, is the sum of static head, HS, and head loss, HF, plus this safety margin. For example, if our static head is 8 meters and the friction loss is 2.3 meters, the total dynamic head comes out to around 10.3 meters. To ensure safe operation, we add that 25% safety margin, bringing us to approximately 12.9 meters. This approach helps us design systems that are efficient and reliable, considering both the actual flow conditions and safety factors. Let's take a closer look at the pump selection for this project. We've chosen the Grundfos SL 1506522 260 GC model for the drainage sump pump. This pump features an S-tube impeller and provides a 15-free passage, which is crucial for handling solids and preventing clogging. It's designed to be reliable and efficient in drainage applications. For the sewage main pump, we've selected the Grundfos SLV 8080110 GC. This model uses a super vortex impeller, which allows for an even larger ADEM-free passage. This is especially important for sewage systems where larger solids and debris are common, ensuring smooth operation without blockages. An important point to note is that each pump set includes 2 units, one for duty and one as a standby. This setup ensures continuous operation and minimizes downtime if one pump needs maintenance or encounters a problem. The sets also come with auto coupling, guide rails, and a stainless steel lifting chain, making installation and maintenance straightforward. Finally, each set is equipped with 4 float switches. These switches are vital for automatic operation, controlling pump activation based on fluid levels and helping to prevent overflows or dry running. Overall, these carefully selected pumps and accessories are designed to ensure robust, reliable operation aligned with the overall system's efficiency and safety standards. Let's take a closer look at our material selection for this project. For the pumps, we've chosen cast iron GG25 with an epoxy coating. This combination ensures durability and resistance to corrosion, which is essential for long-term operation. Moving on to the guide rails and chains, we've opted for stainless steel 304, and we've used 6 meters of it to provide strength and reliability. For the float switches, we selected the Ital Technica IP68 type, rated to operate effectively within a temperature range of 0 to 60 degrees Celsius. This ensures consistent performance in various environmental conditions. The control panel enclosure is made of metallic material with an IP66 rating and is powder-coated, offering excellent protection against dust and water ingress. And of course, all mechanical parts conform to Grundfos quality standards, ensuring we meet the highest levels of performance and reliability. This careful selection of materials ties back to our overall goal of creating a system that is robust, efficient, and durable over time. Let's take a closer look at the control panel and automation system. The system utilizes a duplex DOL starter, which stands for Direct Online Starter, equipped with Schneider components. This setup ensures reliable and straightforward control of the pumps. Each pump has its own control switches, specifically auto, off, and manual. These allow operators to select the desired operating mode easily. You'll also notice run and trip indicators, which provide clear visual signals of the pump's operational status, and a buzzer alarm for fault detection, ensuring prompt response to issues. Float switches play a crucial role here as well. They enable automatic sequencing and provide protection. In essence, they help manage the pump operation based on water levels, preventing dry running or overflows. Now, an important concept to understand is the current calculation for the pump. The formula I equals P divided by the square root of 3 times the voltage times the power factor. For example, a 2.2 kilowatt pump operating at 400 volts with a power factor of approximately 0.9 would draw about 4.4 amps. This calculation helps us size our electrical components properly and ensures the system operates efficiently and safely. Overall, this control setup integrates automation with manual control options, making the system both reliable and flexible for various operational needs. Let's take a closer look at the reference drawings on this slide. What we're seeing here are detailed representations of the entire pumping station, including the basement equipment and the lift station section. These drawings are essential because they give us a comprehensive overview of the station's design and layout. All dimensions shown are in meters, which helps us understand the scale and spatial relationships accurately. On the visual side, there's a 3D composite image of the pump room, which helps us visualize the space in a more realistic way. Alongside that, there's a 2D consultant sheet that features a legend and arrows. These elements are crucial for interpreting the drawings correctly. The legend explains the symbols and components, while the arrows guide us through different sections and points of interest. This slide emphasizes how detailed and precise our planning needs to be, ensuring that every component fits perfectly and functions efficiently. These drawings are a vital reference throughout the project, connecting the design concept to real-world construction. They also help us communicate complex details clearly to the entire team, keeping everyone aligned and informed as we move forward. Let's walk through the installation procedure for this project. First, you want to prepare the wet well base and make sure to fix the auto coupling securely. This step is crucial because it sets the foundation for the entire installation. Next, install the guide rails and lifting chains. These will help you position the pumps accurately and safely. Once that's done, carefully lower each pump into place and engage them with the base coupling. Precision here ensures smooth operation later on. After the pumps are in position, connect the discharge piping and electrical wiring, making sure all connections are tight and properly insulated. Finally, adjust the float switch levels and perform a seating check to confirm everything is aligned correctly. This comprehensive approach not only ensures a proper setup, but also helps maintain system reliability over time. Remember, each step connects to the overall theme of ensuring efficient and safe pump operation. Now, as we approach the handover stage, it's crucial to ensure everything has been thoroughly tested and commissioned. First, we perform a hydrostatic pressure test on all connected piping to verify there are no leaks and that the system can handle the designated pressures safely. Next, we check the electrical insulation and rotation of the equipment to ensure everything is functioning correctly and safely. We also perform float switch operation tests for all level controls, which are vital for maintaining proper system levels and preventing overflows or dry running. Additionally, we run auto and manual cycling tests via the control panel to confirm that the system responds accurately under different control modes. Throughout this process, we record important operational parameters such as flow rate, head, current, and efficiency. This data helps us assess the system's performance and identify any issues before handover. And speaking of efficiency, remember this key formula. Efficiency equals the product of density, gravity, flow rate, and head, divided by the input power, all multiplied by 1,000. This gives us a clear metric to evaluate how well our system is performing relative to the energy it consumes. All these steps are essential to ensure that the system is reliable, safe, and ready for operational use. In summary, both the drainage and sewage systems have been designed to meet all hydraulic and electrical requirements, ensuring reliable operation. We've included full standby redundancy, which means that in case one component fails, the system can seamlessly switch to backup, maintaining continuous functionality. All equipment has been carefully selected to comply with industry standards such as SBC 801, NFPA 20, IEC 60204, and ASHRAE 90.1. These standards cover safety, performance, and energy efficiency, giving us confidence in the system's robustness and compliance. Additionally, the Grundfos pumps and Weibull control panels used in this project are approved according to the specifications provided by our consultants. This approval confirms that these components meet the necessary quality and performance standards, reinforcing the overall reliability of our systems. Overall, these points highlight our commitment to safety, compliance, and operational excellence, which are central themes throughout this project.